Let's just review everything we've talked about so far. We started off looking at the general polar form of an equation that describes a sinusoidal steady state waveform. It has some magnitude, we call that an amplitude, times cosine of some frequency multiplied by t. This is its angular frequency measured in radians per second, plus its angle. And as engineers, we prefer to measure that in degrees. So the whole waveform looks like this. We next talked about what the amplitude does. As we increase or decrease our amplitude, it stretches the whole waveform vertically. We next talked about the phase. We said we could measure it in radians or in degrees. In radians, it might go between plus pi and minus pi. In degrees, that would correspond to plus 180 to minus 180. And we said, if we put in this cosine waveform, this pure cosine waveform as a reference, then if we get something that moves to the left a little bit, we can see it would hit every point a little bit early. So we would say that this waveform here leads our reference zero waveform. It leads our reference waveform by a little bit. In this case, it leads it by 36 degrees. On the other hand, if we have a waveform that looks like this, it lags our reference waveform by a little bit. In this case, as I've drawn it, 14 degrees, because it will take a little bit of time lagging it before it hits that same 0 point that our reference waveform hit it right here. I'll give it a bigger lag. Now you can really see that there's a much bigger lag, and that's a 32.4 degree lag. After we talked about the phase angle, we talked about frequencies. And so we said that there's high frequencies and low frequencies. You can measure frequencies either in radians per second, like this is, or we could measure it in 2 pi ft. So, and then the frequency is f, and we could find its time period as 1 over that frequency. So last, we talked about how to convert between rectangular notation and polar notation for sinusoidal steady-state waveforms. And by that, we said that the polar notation we would represent as having some sort of amplitude here times cosine with a phase. And we compared that to the rectangular notation, which was some amount of cosine with no phase minus some amount of sine with no phase. And we drew a picture much like this to help us convert between the two forms. And we said that right here you can see there's maybe about 0.88 amount of cosine. This is how much pure cosine there is, and that's what our rectangular notation shows, about 0.88 of cosine. And similarly, you would subtract from that barely less than a half of sine, and you're subtracting barely less than a half of sine. And that corresponds to a polar notation amount of the length of this line. So this is 1, so it's about 1 cosine, and this angle is maybe 30 degrees or so, and when you look at it, we see it's exactly 29 degrees. At this point, don't worry about phasor notations or complex exponential notations, but if you want to, you can see how similar the complex exponential notation is to our polar notation. It's almost the exact same thing, except instead of a cosine, we just raise things to an e to the j power. More about all that in our next lesson.